Hi folks, I'm going to go quickly through some solutions to some of our homework problems. So this is from page 146 and it's number 12. And they want us to show that this line is tangent to this particular curve. Okay, so in order for this line to be tangent to the curve, it means that the slope of the tangent line must be equal to the rate of change of the curve at that point, and they have to share the point at that x value. Okay, so the first thing is let's find the x value when this curve has the slope of this tangent. So first I'll rearrange this. Y equals 4x plus 11, so the slope of the tangent is equal to 4. So I need to determine when this derivative is equal to 4. Okay, so let's start by taking the derivative here. So y prime is equal to, so 16 is just a constant, and this is x to the minus 2, so the derivative is negative 2x to the minus 3, and derivative of 1 is equal to 0. Okay, so this can reduce to negative 32 over x cubed. Okay, so let's now solve the equation for equals negative 32 over x cubed, since we need to know when the derivative is equal to 4. Okay, so I'll bring the x cubed to the other side, divide the 4 on the right, so negative 32 divided by 4 is negative 8, and so here the cube root of negative 8 is just equal to negative 2. Okay, so when x is equal to negative 2, the slope of the tangent to this curve is equal to 4. The last thing we have to do is show that they share a point when x is equal to 2. Okay, so I'll call this y1 and I'll call this y2. So first let's check the y value on the line. So 4 times negative 2 plus 11, so negative 8 plus 11 is 3. Now we need to make sure that the y value is the same on the curve. Okay, so here we've got 16 over negative 2 squared minus 1, and so 16 over 4 is 4, minus 1 is 3. Okay, so we've shown that this tangent shares a point with this curve when the rate of change of the curve is equal to the slope of the tangent. So we've done our job. Okay, so in a second we'll go to another question. Okay, next question is page 50, number 8, and they want us to show that this function here has no tangent with a negative slope. Okay, so if we want to find the slope of these tangents, first thing we have to do is find the derivative, and hopefully once we do that, we can see whether we can make this determination or not. Okay, so here I'm just going to use the quotient rule, so derivative of the numerator, which is 5, times the denominator function, x plus 2, minus the numerator function, 5x plus 2, times the derivative of the denominator function, which is just 1, and all that over the derivative squared. Okay, so let's simplify that here. We've got 5x plus 10 minus, okay, this is where you want to be careful, make sure you're subtracting, you always open up a bracket just to make sure. So 5x plus 2, that doesn't change, and here x plus 2 squared, and now let's simplify. 5x and 5x cancel each other out, and we're left with 10 minus 2 is 8 over x plus 2 squared. And since the numerator is a fixed number which is positive and the denominator is squared, so it has to be positive, this here is strictly, actually we should say strictly greater than 0, because it can never be equal to 0. So since the derivative is always bigger than 0, we can never have a tangent with a negative slope. Okay, that's it for this one. Next one in a second. Okay, so the next question is 9b from page 150 again. They give us this function. They want to know when the tangent is horizontal. Okay, so in other words, we need to determine when the derivative is equal to 0. Now, you can work with this function as is, but if you take a look, x squared minus 1 is nice and factorable, and so is the denominator. So it'll be interesting to see if this actually simplifies. And when we factor everything out, we see that it indeed does simplify. Okay, so here we have x plus 2 and x minus 1. So here the x minus 1's reduce, so we're left with y equals x plus 1 over x plus 2, okay, if x not equal to 1. Okay, now it's important to keep this restriction here, so you know that there's going to be a hole at x equals 1, but any conclusions we make about this function, we have to keep in mind we're always talking about that original function. By the way, this would work perfectly well if you stuck with the original one, just the algebra would be a little more complicated. Okay, so now let's find the slope, the derivative of this function here, because again, other than at x equals 1, these two functions are exactly the same. So let's take the derivative here. So we have the derivative of the numerator, which is 1 times the denominator function, x plus 2, and then here minus the numerator function, x plus 1 times the derivative of the denominator, which is just 1. Notice how I write it out all the time, just so I never forget to do so. Okay, so x plus 2 squared. So let's simplify this here, and we have x minus x is 0, and then we're left with 2 minus 1 is 1. Okay, and we're left with 1 over x plus 2 squared, and we want to know when that is equal to 0, and there is no solution for this question here. Okay, so you'll notice that the back of the book has an error in it. It does have a solution. I suspect they perhaps forgot, they might have worked with this original function and forgotten that the function is not defined at x equals 1, because I think that's what the answer is. So in this case here, we've shown that the derivative can never be equal to 0, so there's never a horizontal tangent. Okay, if you ever want to check something like this out, just sketch the function in Desmos, and you'll see that that is certainly the case. You'll also see that the derivative is always going to be positive. Okay, that's it for this one. Back in a second. Okay, next question is number 10 on the same page, and what they give us here is a population function for a group of bacteria with an initial population of 1,000. And they want to know the rate of change at t equals 1 and at t equals 2 hours. I'll just do t equals 1 since t equals 2 just means you input another number. Okay, so since we want the rate of change, we're going to be finding the derivative of this population function. Okay, so here we've got 1,000 is just a constant, so I just leave that out. Okay, so it'll be 1,000 times the derivative of this function in the bracket. So the derivative of 1 is just 0. Don't need to consider that. So now I'm going to use the quotient rule on what's left over. Okay, so the derivative of the numerator is 4, and I multiply that by the denominator function. Okay, then minus the numerator function, 4t, and multiply that by the derivative of the denominator function, so 2t. Okay, and all of that over t squared plus 50 all squared. Okay, so let's simplify that a bit while we're at it, just make the evaluating a little easier. Okay, so here we've got 4t squared minus 8t squared, so that's negative 4t squared, and then plus 4 times 50 is 200, all over t squared plus 50 squared. Okay, so in the end, we have to calculate now p prime at 1, so it's just a matter of inputting this into our derivative equation. So 1,000, okay, so here we're left with negative 4 times 1 squared, so negative 4 plus 200 is 196, and here we're left with 1 squared, so 1 plus 50 all squared, so 51 squared. Okay, and here we'll have to grab our calculator and check this out. So what do we have? We have 1,000 times 196, and then divided by 51 squared, and we've got, looks like about 75.4. Okay, so this is approximately equal to 75.4. Now, because there's a context here, we really should be giving units, okay? And so the population is number of bacteria, and the time is in hours, so this is going to be 75.4 bacteria per hour, okay? So we've got that the population of bacteria is increasing at 75.4 bacteria per hour. Okay, that's it for this one. Let's, in a second, move on to the last one. Okay, folks, the last question we're going to look at is number 11, still from page 150. So they want us to find the equation of the tangent to this curve at x equals 2. So in order to find the equation of the tangent, we need a point and we need the slope. Okay, so let's find the point. So since x is equal to 2, and the curve as well as the tangent line will share the same point, we just have to calculate y at 2 to find a point on the curve and the tangent line. Okay, so 2 squared minus 1 over 3 times 2. So that gives us 4 minus 1 is 3 over 6, so 1/2. So we know the point 2, 1/2 is on the curve. So now let's go and find the slope of the tangent. So first we need to find the derivative of our function here. So we've got the derivative of the numerator is 2x times the denominator function, 3x, minus the numerator function, x squared minus 1, times the derivative of the denominator, which is 3, and all of that over 3x squared. So we'll simplify here. So we've got 6x squared, and here we've got minus 3x squared and plus 3, all over 9x squared. And so here we're left with 3, oops, that's x squared there, 3x squared plus 3 over 9x squared, and factor out the 3 here, so we're left with x squared plus 1 in the numerator, and the 3 in the numerator reduces with the 9 in the denominator, so we're left with 3x. Okay, so now we'll find y prime at 2, since that's what we need. So 2 squared plus 1 over 3 times 2 squared. So we're left with 4 plus 1 is 5, and 3 times 4 is 12. Okay, so now that we have our point and we have our slope, we can find the equation of the line. Okay, so 1/2 is equal to 2 times 5 over 12. Okay, there's our x and y and our x and y and our slope, and then plus b. So here we're left with 5 over 6, so b is equal to 3 over 6 minus 5 over 6, so b is equal to negative 2 over 6, so b is equal to negative 1/3. Okay, and so here we've got our final answer, y is equal to 5 over 12x minus 1/3. Okay, so again, because the tangent line and the function share a point, we can use a function to find the point, and then we use a derivative to find the slope. Okay, and that is it now for today.